Today, Australia consumed 18 million liters of jet fuel. That's enough to fill our campus pool 7 times. Now, half of today's fuel came from somewhere other than Australia. So let's just imagine that tomorrow we wake up and we can't find any more oil here, and no one will sell us a single drop. Your 2-hour flight to Sydney will now take you 3 months to walk. Access to oil in the future is not a guarantee, and this is a global problem. One way to address these challenges are for industries to come up with sustainable alternatives to petroleum right here in Australia. I'm involved in a project that's trying to turn Australian sugarcane into renewable jet fuels. To do this, we're using an ancient technology, but with a twist. Now, we all know that yeast can turn sugar into beer and wine, but instead of making ethanol, researchers are rewiring the yeast metabolism to make a jet fuel. So what do yeast and jet fuels have to do with oranges? When you open an orange, what you're smelling is an oil called limonene. Limonene is a hydrocarbon that has excellent jet fuel properties. In fact, limonene outperformed traditional jet fuels in a test flight this past June. Now, it's impractical to just go consume the world's orange supply. So that's why researchers are taking genes from oranges and assembling them in yeast to try to make tiny limonene factories instead. 3 years ago, I sat where you are. I looked at this technology and said, all right, they're trying to make yeast cells that spit out orange-flavored jet fuels that are going to save the world. This sounds too good to be true. And I was right. There's a major problem facing this technology, and that's the fact that limonene is toxic to yeast cells. When you go to the supermarket and you buy dishwashing liquid and it smells like lemons or oranges, those flavor compounds aren't just there to smell nice. They actually help kill bugs. So the past 3 years, I've been developing strategies to help this technology work. First, I redesigned the bioreactor so that as soon as the fuels are produced, they immediately get removed. This now allows us to achieve up to 700 times the concentration of these fuels compared to a traditional reactor design. Second, I engineered the cells to be more resistant. I combined biology's oldest tool in adaptive evolution with today's modern tools in genome sequencing. Now, we only have 3 years to finish a PhD, so I couldn't sit around and wait for the yeast cells to evolve naturally on their own. So I sped up evolution in the lab. Each day, I'd give my growing yeast cells 2 things: fresh food, and I'd challenge them with a little bit more limonene than they had the day before. This constant environmental pressure ensured that only the fittest cells survived each day. 2 months later, I isolated a yeast strain that was much more resistant than the one I started with. I then used genome sequencing to give me a very specific roadmap of the yeast DNA to show me exactly what had changed during evolution. Now, by changing only a single gene, I can improve the cell's resistance to these fuels by an order of magnitude. My PhD work is bringing renewable jet fuels in Australia one step closer to reality. So the next time you open an orange at lunch, you can tell your friends that what they're smelling is a fuel for the future.